Hello, my name is Indiana Renfro. Welcome to PHYS 2212, Lab 5, Baking with Faraday. Introduction. The purpose of this lab is to practice and study Faraday's law. In this lab, we'll observe a falling magnet, source of external field, through an aluminum foil, induce current, and observe their interactions. By the end, we'll have collected observation data of a magnet falling through a conductive tube of aluminum foil and modeled the magnet tube interaction computationally and compared the two sets of data. The result of the experiment was 1.39 seconds, and the computational data was 4.5 seconds. Main concepts and equations. There are three main concepts in this lab: Biot-Savart's law, Faraday's law, and the EMF, flux, and Ohm's law, accompanying it with Newton's second law. In the experiment itself, the model of the system and surroundings is the magnet falling. The magnet is the system, and the aluminum foil being the surroundings, and model a magnetic dipole and a conductive tube. Some assumptions: the only forces on the magnet are the force of gravity and the force from the loop. And the procedure was first mark the north pole of the magnet using a magnetometer at, measure the length of the lift in the aluminum foil, then record the drop in the magnet through the tube, and then finally rewatch the video of said recording and find where the magnet enters and leaves the tube, calculate the amount of time between the two events. Repeat this 5 times and calculate the average. Aluminum foil measurements: the length of the foil was 0.30 meters, the width of the tube was 0.006 meters, the inner radius was 0.0117 meters, outer radius of the tube combined with the width and inner was 0.023 meters. In the 5 trials, and the first was 1.39, second 1.36, third 1.41, fourth 1.40, and 1.38 seconds, coming to an average of 1.39 seconds for our experimental model. For the computational, you can see our physical constraints for our plots. And then the first step was creating the tube of aluminum, where we added the length, width, inner radius, and other parameters. And then we added more to the tube, and then we started adding like the mass. And right here is the magnetic dipole from lab 3. And then we go on and set more initial derivatives, and then we set the dipole B to calculate the magnetic field of the bar magnet. And then after calculating the bar magnet, we set up code to create magnetic flux. Then we create a simulation loop where it's predicting the motion and visualization of the bar magnet falling through the tube of aluminum foil, as you can see here, and we calculate it within rings, and then eventually we plot it, and the results come out to look like this. This is the tube that created through the code, and this is the velocity versus time as the magnet is falling through the tube. And as you can see, the time of the tube became 4.493 seconds, which rounds up to 4.5 seconds. Some computational questions: the intensity of the coloring of the tube indicates the magnitude current flowing through each ring. Red and blue indicate currents flowing in opposite directions. Which code corresponds to clockwise and which one counterclockwise? And how can you know? The red represents counterclockwise, and the blue current represents clockwise. We know this from Lenz's law. What happens to the dynamics of the system when you flip the magnet around? The only thing that would change is the direction of the current. How does the total time in the loop of your real-world scenario compare to your computational one? How might the computational system be more accurate? The experimental time was shorter, the trial and the computed time. And we made the computational system more accurate by splitting the tube into rings and reevaluating the magnetic dipole from lab 3. And as the shape of the velocity versus time will tell you that the force is acting on the bar. The shape of the graph tells us the gravitational force starts out strong and gets canceled out for the duration of the tube and then becomes strong again. Comparisons: they're labs from the results. As we saw, experimental was 1.39 seconds, and the computation 4.5 seconds, and this makes a difference of 3.11 seconds between the two labs. Possible sources of error: as there could have been a miscalculation for the magnetic dipole from lab 3. Errors is not being accounted for, and the friction between the tube as the magnet falls down as it hits the sides. Conclusions: what if the resistivity of the conductor reduces close to possible to 0? How can the dynamics of the falling magnet change? This would cause there to be a larger current, and this would make a larger magnetic force, causing the magnet to slow down and falling in the tube. And what if there were holes or slots cut into the tube? How would this affect the ring current in your model? Holes or slots in the tube would reduce the induced current, as a result, decrease magnetic force from the loop, and this would increase the speed as the magnet as it falls. Thank you for your time.